thing is it says a group of 12 companies in the insurance industry has a mean annual profit as percent of revenue of 4.4. So that's how much revenue they get. That's 4.4% with a standard deviation of 1.6. While the mean annual profit as a percent of revenue for a group of 10 healthcare companies was 4.6 with a standard deviation of 1.4. Okay. Find a 90% confidence interval for the difference in their mean annual profit. And then it says, at the 90% level of confidence, does it appear that one industry group has a higher profit as a percentage of revenue? So basically, we're going to find, after we find that interval, we're saying, is that interval all positive, all negative, or is zero possibly included in the interval? If zero is possibly included in the interval, then we can't say that it appears that one group has a higher profit. But if zero is not in the interval, then we can maybe say which group would have a higher profit. All right, so we'll start with P, and we're going to say we would like to find, and it's right here, the difference in mean annual profit between the insurance industry and healthcare companies. Okay, and so we've got to label our two means. So mean 1, x bar 1, mean 1 is going to be, we'll go in order usually, it would be the insurance industry. So you have to tell, you can't just say mean 1 is this number. You need to tell them, hey, the first one's going to be the insurance industry. And the insurance industry has a mean of 4.4. And then a standard deviation, we'll call it standard deviation 1, of 1.6, okay? The next one, mean 2, is going to be the healthcare companies. So we say healthcare. And it has a mean of 4.6 with a standard deviation of 1.4. Now, if I was just guessing, I don't think there's a big difference between these two, because just looking at the numbers, it looks like the insurance industry is about 4.4% and the healthcare industry is 4.6%. That's pretty close, right? That's only 0.2% away from each other. So we're probably going to have difficulty proving that one is higher than the other. So, but you can see that already when you start the problem. Now, A is our assumption. So in our assumptions, remember, we have to make sure, number 1, that it is random. And for random, we see, do we see it's random?
No.
No, I don't see it. So random is not stated. Okay? So we go to number 2. And we see it's independent. We're going to assume there are more than 120 insurance companies, which we know there are, and more than, what's our sample size of the other one? 100 healthcare companies. Okay, and just so you know, in the P, you have X bar and the standard deviation. You can go ahead and put N in there also, because you know when you plug in the calculator, you're going to need N. So N is 12, right? And the first one, N1, and N2 is 10. It means the sample size for the second one, which is the healthcare companies, is 10. Now, the third assumption is the normal one, okay? And this one's going to fail our normal condition, right? Because the central limit theorem says N must be at least 30 for it to be normal. We have 12 greater than or equal to 30, that's an X, and then we have 10 greater than or equal to 30, that's another X. So it doesn't pass that either. Okay, it did pass the independent condition. So it failed the random condition because they didn't state that it was random, and it failed the normal condition. So now we go to the name of the interval, and this is called a 2-sample T interval. Okay, so it's two samples because obviously we're talking about two different things. We're talking about the healthcare industry and the insurance industry. And so now we're actually able to go, I'm going to go over here to I. We're able to actually go and get our interval. All right. So you need to go to, we're going to go to the calculator for the first time for these, and we will get the interval for this two sample T.
Did we do one sample T?
Yes. Yesterday was one sample T. Was just, and that's just called T interval. If it's one sample. All right. So two sample T interval is number 0 down there. Okay, so I'm going to click on that, and it asks, do I have data or stats? So the data would be if there's stuff to put in list 1 and list 2. We don't have stuff to put in list 1 and list 2, but we do have the statistics for this. So the mean of the first one, that's why you want to write that in the parameter MP so that you already have all this stuff when you go to the calculator. Okay, so mean 1 is 4.4. And make sure you're putting it in correctly in order because a lot of people will put a number in the wrong one, and that's going to really mess you up. Standard deviation is 1.6, and then the sample size is 12. In the second one, the mean is 4.6, standard deviation is 1.4, and the sample size is 10. These are small samples, right? And we want to be 90% confident. Okay, pooled, you just leave it at the default. It's no. Okay, and that's something we don't have to talk about in this. All right, so calculate. Now, as you calculate that, we get negative 1.3042.90364. That's our answer. That's our interval. Now, if you notice, that interval goes from a negative to a positive. So 0 is in the interval. So that is important when we get to our conclusion, that 0 was in our interval. Because what the question's asking at the end is going to be answered by that. Okay? So, that's where we're going. So, this tells us we're 90% confident. We are 90% confident. Here goes the long conclusion. We're 90% confident that the true mean difference between percentage of revenue in insurance companies and healthcare companies is between, and this is, remember, percent of revenue, so how much, so it is between negative 1.3004% and 0.90364%. Therefore, because 0 is included in the interval, so what happens when 0 is in the interval? When 0 is in the interval, it means that the difference between the two could be 0. That's a plausible or possible answer. So because 0 is in the interval, the difference between the two could be 0. So that means where it says, does it appear that one industry group has a higher profit or has a higher percentage of revenue, we could say, therefore, because 0 is included in the interval, we cannot say that one group has a higher percentage of revenue. Okay? So we're not able to say that. Now, if the entire interval would have been negative, okay, then that would mean that the second group had a higher percentage of revenue. Because if you subtract two numbers and you get a negative, it means the second number was bigger. Okay? So if the entire interval would have been negative, we would have been able to say the healthcare companies, the second group, had a higher percentage of revenue. If the entire interval would have been positive, we would have been able to say the insurance companies had a higher percentage of revenue. But since the interval includes 0, we're not able to say. And usually in my conclusion, and some people do it in every single one, in my conclusion, I always talk, when I'm talking about two things, about 0. I'll say, therefore, because 0 is included in the interval, we cannot say a group has a higher revenue. I might even say, if it would have been all negative, I would have said, therefore, because 0 is not in the interval, we can say that healthcare companies have a higher percentage of revenue, right? So that is, our interval is leaning towards the negative, right? It's closer to the negative than it is the positive. Like, it's going that way. Because the healthcare companies have a higher percentage in our sample. But why is 0 still included in the interval? Where there's a couple reasons. Number one, we talked about their two means are very close together. 4.6 and 4.4. They're only 0.2% apart from each other. Their sample sizes are very small. We've only looked at 10 companies and 12 companies. So to see, if you really want to see a difference between them, you're probably going to need a bigger difference here and a much larger sample size than what we have here. Okay? So that's things that kind of restrict you. It restricts you if your data is close to each other. But, maybe the person doing this was trying to prove that the two industries had basically about the same percentage of revenue, like same profit. So it didn't matter if you were in the healthcare industry or the insurance industry, you were at about the same profit level. Number 6, a sociologist is studying the size of rural Canadian families. The number of children in each family is noted for low-income families and high-income families. Compute a 95% confidence interval for the difference in the mean number of children from low and high-income families. Does there seem to be a difference in the average number of children in low or high-income families? So that's at the end, but the 0 we're going to see if there is. Typically, what we would expect to see is more in low-income families, like just because that would just be the expectation from society, but that's not always the case, so we don't know that. So when we start a test, typically they have in their head, and this kind of relates back to science, right? Because you have a hypothesis. But typically, when they're doing something like this, there's a reason they're doing it because they have a theory that they think is true. But you can't just think something's true. You have to actually go through and give the statistics and have the data for it. It's kind of like when they think they have. There was a good one about the vaccine trials that they were doing. They thought that it was so effective, but they had to go through and they actually had to sample 30,000, and I was looking at it, we can look at it later, but they had to sample 30,000 people to get the trial to even go through the first step of approval. So they had to get 30,000 people. Not only did they have to get 30,000 people, they had to get so many minorities, so many over 65, so many with health conditions, so many in good health, so many younger.
Incredibly young.
Right, so they had to get so many of each bracket and make it diverse, and then they had to compile the results separately to make sure it doesn't the vaccine doesn't hurt young people, or it doesn't hurt elderly people, or it doesn't hurt minorities, or it doesn't. So they had to check all those. Then they had to compile all the results together, and so before they can even come out and say that it might be effective, so they had to go through a massive process just to get to that point. That's just to get to that point. And then all that does is get you to the next step of the process.
And you got to do it all over again. Basically.
Yes, and with the even bigger sample. So you start with 30,000. Now you're going to go to 100,000. Yeah, and so then eventually, if you can get it on a large scale, then it can be mass distributed or whatever. But all right, so high and low income families. So P is the parameter of interest. We're interested in the difference in average, and this is the what? Number of children, average number of children in high and low income families. And remember, this is in Canada.
It's
In rural Canada. Yeah, exactly.
10 children? Oh my God.
Okay.
Oh,
All right. So number one. So remember, the first one is going to be, we're going to say is low income because that comes first in the table. The second one we're going to say is high income. So in low income, we're going to call that X bar 1 and the standard deviation 1 and N1. And in high income, we have X bar 2, standard deviation 2, and N2. All right, so
It's up there.
we're going to need all that stuff, but we're not going to get that yet. And that comes from the calculator. The calculator is going to give us all that. All right, so let's go to A, the assumptions. Number 1, random. Here, nothing about it. Okay, number 2, independent. We assume more than, how many low income? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We assume more than 140 low income rural Canadian families. Check. Now, your N1 is 14. I just counted that, right? So you can fill that in. High income is 16. 1, 2, 3, 4, 5, 6, 7, 8. Yep. So we assume that there are more than 160 high income rural Canadian families. Lots of writing in these, but that's okay. All right, so there's your assumptions. Number 3 is that it's normal. We have a central limit theorem n greater than or equal to 30. Again, we're dealing with small sample sizes here, which is okay. Just means that it's not approximately normal, which is fine. It's not a big deal. We just have to note it. So 14 greater than or equal to 30, we put an X. 16 greater than or equal to 30, we put an X. These are small scale. These are small scale samples, so they're not passing the central limit theorem right now. When you're talking about, like we were talking about, like a vaccine that has 30,000, then obviously it's passing it by far. So typically, like, if they're big scale experiments, they're passing that central limit theorem easily. But because this is kind of like just one sociologist that's studying rural Canadian families, maybe he just looked up some data that he had, because it doesn't even say that it's random. So maybe he just found some people or some families that he
Could
knew.
this be like totally biased?
It could be, yeah. Yeah, so could be biased because it's not stated that he randomly got the numbers, and the sample sizes are small, so it can definitely be biased. All right, so there's your A. N, this is a 2-sample T interval. So we've got that, same as we had with the last problem. And now we're actually able to go do the interval. Now, to do the interval, you need to put the data into list 1 and list 2. So that's our next step, is we've got two things, the low income and high income, and we need to put them into list 1 and list 2. So stat edit, and we had numbers from when we did 1 from the T interval. Now we're looking at the 2 sample. So a lot of numbers to type in because you got 30 total. The order you type them in does not matter. So somebody asked, like, should I go up or down? It doesn't matter. Just get the right numbers in there. Let's see if I can get the right numbers in there too.
If pooled, still no.
Correct. All right, I'm in list 2 now. So 7, 1, 3, 5, 4, 3, 4, 2, 4, 1, 1, Yeah. What are the last two for high income that are covered up by my calculator?
On the right, 4 and 5.
4 and 5?
Yeah.
Okay, so I've got them both in there. There's 14 in list 1 and 16 in list 2. So I'm going to stat test. We're going to go to number 0, which is the 2 sample T interval. I'm going to hit enter. Oh, I did letter A. I went too far. All right. That's why I couldn't tell. All right, so we're going to go over to data because we have data, not statistics. And it automatically is set up to be put in list 1 and list 2 on your calculator. So you've got L1 and L2 as your 2 lists. You've got the frequency. You want them ran 1 time each. And you want your confidence level. What did it say in this problem? 95. That's the default normally. So 95%. We don't pull it, and we calculate. All right, so calculate is going to give me, is that what you got?
Yeah.
Negative 1.314 to 2.6537. So 0 again is included in the interval, which again is not going to give us the difference between them. Now, there may be a difference. So let's go fill in the mean and standard deviation for these. So for the first one, 4.86, and the standard deviation for the first one is 2.77. For the second one, 4.19, if we round it to 2 decimal places, and 2.48. Now, so if you notice, the high income families do have less children, but it's not a huge difference. It's only from 4.86 to 4.19. And our sample sizes are small, so the interval is not really picking up a big difference. So see our conclusion. We are 95% confident that the true mean difference in average number of children between low and high income rural Canadian families is between negative 1.314 and 2.6537. Therefore, because 0 is included in the interval, we cannot say there is a significant difference. Because like I said, there may be a difference. It may show in our data that there's a difference, but it may not be a significant enough difference between the two. And again, things that are hindering us in this is the fact that low income averages 4.86, a little bit under 5. High income still averages over 4. So they're very similar. And we only had 16 and 14 in our sample. Now, if we had 160 families and 140 families in our sample, and we got that big of a difference, then we're probably going to have some conclusive results there. But because we didn't. Now, somewhere in this sheet, you should end up, I'm sure at some point, you will get a problem where 0 is not included. Remember, if it's all positive, that's going to tell you that the first one is bigger, is higher, whatever the problem's talking about. If it's all negative, it's going to tell you the second one is higher. So you want to address in that last sentence of the conclusion, because 0's in the interval or because 0's not in the interval, whether you have enough evidence to say one's higher than the other. Okay? So I've done 2 of those. There were 6 total problems on there. I've done 2, so there's 4 left to go in the 2 samples. So you finish that up for today's work, and that's it. And that will take us through all the intervals. So it's a good stopping point that it's the end of the week. You have all the intervals done. Next week, we will start with 1 proportion z-test and go through that. That'll take 2 days because we're going to do that slowly. 1 proportion z-test, just so we learn a test. And once we learn a test, then when we do a 2 proportion test and a 1 mean test and all that, it's going to be the same kind of setup. So we're going to learn what is a hypothesis test and start with the 1 proportion z-test next week. All right, so let's finish those 4, and that will be the rest of today.